recording through all of that setup process. Doesn't matter. This is where we left off. We have our function. We graphed it. We know we have a discontinuity at x equals 1 because of this division by 0 right here. So here's my table. And this is how your homework's going to wind up looking. You're going to be asked to solve a problem numerically, evaluate a limit numerically. This is what I expect to see, including the discontinuity, which we know is going to be undefined. Now we're going to, with our table on our calculator, enter in all these values here and then analyze what those values are doing. So let me bring my calculator back up here. Okay, at 0.97 I have 2.9109 and so on. So I'm just going to fill in all these values here all the way down and then continue on across. And it's going to be kind of hard for me to do that since this will drop to the other. Let me see if I can tell it to be always in front and maybe that'll help. So we have 0.9109, 2.9404, 2.9701, and then I need to 3.0301. Okay, go ahead and tell me the rest. Okay. Okay. So then what you're going to do is you're going to say, all right, as we approach our discontinuity from the left, so 0.97, 0.98, 0.99, what is our function tending to do? Like what number is this sort of approaching? It's approaching 3. So from this side, I'm going to say the limit as x approaches 1 is 3. From this side, what number do we seem to be approaching? 3. So I'm going to say the limit as x approaches 1 from this side, and there's notation that I'll introduce here in this chapter a little bit later, but for right now, equals 3. So we're approaching the same number from both sides. Because we're approaching the same number from both sides, we can say that the limit as x approaches our discontinuity overall is 3. If we did not have the same number approached on both sides, then the limit would not exist. Okay? All right, let's see if we can do the same thing now with this problem. So where should we start? That doesn't matter anymore so much. We're going to be too worried about rudeness. So the directions actually tell you to do that first and then estimate the limit where that function is discontinuous. Okay, so that's where we're going to start. I don't care that I have a square root in the denominator here. Again, we are going to be so consumed with other things in this class that something as trivial as this, most of the time, we're going to ignore. So we need to find where that denominator is equal to 0, right? X equals what?
1.
So if I cover this up, I'm going to have something minus 1. That something has to be what? Has to be 1. So now let me uncover that. What do I have to have here in order to make 1 here so that 1 minus 1 is 0? It has to be 0. 0 plus 1 is 1. The square root of 1 is 1. 1 minus 1 is 0. Okay? If you can't do that in your head, then take the denominator, x plus 1, minus 1, and set it equal to 0. And now solve for x. Add 1 to both sides. Square root x plus 1 equals 1. Square both sides. X minus 1 equals 1. So then you get 2. Terrible. What did I do wrong? I changed what sign? Oh, that's a plus. Plus, plus. Okay, equals 0. Thank you. Yep, that's a plus. So it does work out to 0. Anyway, you get x can be equal to 0. So that means we want to evaluate the limit as x approaches 0. Okay? Now, in order to do this numerically, there's no way that you're going to sit there and compute this without a calculator, which means you're going to be using a graphing calculator, which means you're going to graph this and then make the calculator compute everything for you. So we're going to enter this thing into our graphing calculator, bring up the table, center it at 0, and do a step of 0.01. Okay, so we see the graph is sort of a square root looking type function. It's not actually a square root function because the square root is in the denominator, but it kind of looks like that graph. And we know that we have a discontinuity at x equals 0. On my calculator, my table didn't change for me, so I need to change that. So I'm going to go back to my table and menu, table, edit table settings, and I want to start where? 0, and my table step is good. So I hit OK, and then I'm going to scroll up a little bit. 3 things on the left, 3 things on the right of my discontinuity. So here we go. I'm going to start at negative 0.03, negative 0.02, negative 0.01, and then of course 0, and then 0.01, 0.02, and 0.03. We know we're undefined here. Bring my calculator back up, and we have 1.98489, 1.98995, 1.99. Yes, you do. 499. No, you can't. 2.000499. 2.000995. The decimals do matter. And finally 2.01489. All right, so as we approach from the left-hand side of this table, what number does it look like the function is tending towards? 2. And as we approach from the right, also 2. So therefore the limit as x approaches what? 0 equals 2. I'm implying this function right here. If you want, you can write of f of x. That's probably a better thing to do. Let's not be sloppy. So the answer here is the limit as x approaches 0 of the function equals 2. So that means on my graph, when I look back at my graph, I can see 2 on here. The function is approaching, I can see 0 on here. The function is approaching 2 right there. If I were to zoom in over and over and over again, and I could somehow get this to zoom in so that I could actually see the pixel that has x equals 0 on it, that pixel will not be lit. There's a hole there. Right? Okay. All right, sometimes a function obviously has discontinuities without division by 0. And the best example of that would be a piecewise function. It's not so bad. All this says is, I don't know why that happened. All this says right here is this piece is alive when x is not equal to 2. This piece is alive when x is equal to 2. Okay? So my function f of x does this. X not equal to 2, the function is at 1. That's a horizontal line through the y-coordinate of 1 until I get to x equals exactly 2. There's a hole there. It drops down at exactly 2 to 0. And then it goes back up to my function, my top function, and continues. That's the piecewise function. So it's important to understand how this thing is built. Once you do, then you can probably figure out what the limit would be at this discontinuity. Notice it is a discontinuity, but we are not dividing by 0. It makes it a piecewise. Okay? So as we approach, as x values get closer and closer and closer to 0, what number is this function approaching? 1. Good. As we get closer and closer to 2 here, from the other side, what number is my function approaching? 1. So the limit as x approaches 2 of f of x equals what? 1. What's the value of the function at x equals 2? 0. So the limit and the value can be two different things. They don't have to be exactly what the function is.
The value you just plug in.
The value you just plug in. That's right. The limit, you have to evaluate what the function is doing as you approach that x coordinate. All right, so that was an example, or those have been examples of when a limit exists. So now we need to talk about when a limit fails to exist. First, the function approaches different values at a discontinuity. So let's graph the absolute value of x divided by x. So here's my graph on my calculator when I enter it in using the absolute value template. We can reason our way through this, let me get rid of this, instead by picking values for x. If I pick -2, what do I get here? 2. And then here is -2. 2 divided by -2 is -1. So I'm right there. If I take -1 and plug it in, what do I get? 1 divided by -1 is -1. Is it reasonable to say that no matter what number I pick over here, I'm going to wind up with -1? Yeah. So going this way, I'm at -1 until I get to where? 0. At 0, what happens? Can't divide by 0. Does the function jump somewhere and then I can divide by 0? There's not an asymptote. I can't be at 0, right? Now if I start plugging in positive numbers, I have +1 divided by +1, which is +1, so I'm up here. +2 divided by +2 is 1, so I'm here. It's reasonable to say that I'm going to be at 1 everywhere over there, except when I get to 0. I'm going to be open there as well. So is the function discontinuous? Yes. What number do we approach as we are coming in from this way? What number do we approach as we come in from this way? We're not approaching the same number. Since we're not approaching the same number, the limit does not exist. Okay? Okay, the second one, the function approaches an asymptote. This is the one that you're most familiar with. The limit as x approaches 0 of 1 over x squared. What does that graph look like? Doesn't look like a parabola. Well, I guess we better graph it. We know we have a vertical asymptote at x equals 0, so I'm going to draw that in there as a dotted line. We're going to draw lots of vertical asymptotes this year. Because it's x squared, no matter what number I plug in, I'm never going to wind up with a negative value. Okay? And if you can remember how these things look as they approach asymptotes, generally it's going to look like this. Okay? Now, as x, so I'm just going to be kind of formal here, as x approaches 0 from the negative side, I want you to see this notation right here. I'm putting a little negative sign up in where the exponent would be. I'm just saying as x approaches 0 from the negative side. What's happening? So my function goes to infinity. So as x goes to 0 from the positive side now, so now I'm coming in from the positive side, what's my function doing? It's approaching positive infinity. Well, both sides are approaching positive infinity, so does the limit exist here? No? Why? Infinity is not a number, right? It's an idea that the numbers never stop. The idea of a limit is we wind up with a number, a specific number. And here we're not going to get a specific number. So the limit does not exist here either. It does if you're not at an asymptote. The limit does not exist. The function oscillates infinitely as it approaches the discontinuity. So we have a discontinuity here. 1 divided by 0 would give us division by 0, right? So then we'd be taking the sign of division by 0. What happens as you zoom in, and it's kind of hard for even this graphing utility, I was using Geometry Sketchpad for this, to show what's going on. So you can see that it's oscillating kind of like it starts off and then it's like more intense around 0. I zoom in, and it starts off and then it's more intense around 0, and then it can't even graph that really. It doesn't know what to do there, so it just leaves a hole. And then as I zoom in even more, it really got confused really what's going on here is it's getting more and more and more oscillations to the point where it doesn't even know what to do anymore. Okay, so if I would just keep zooming in, I would just keep seeing the same graph over and over and over again. No matter how close you zoom in to 0, you will always see this exact same thing. It's infinitely oscillating as you get closer to 0. In that case, there is no limit, or I should say the limit does not exist here either.